what I'm attempting to do here, I want to start with this analog to digital conversion. I'm going to talk about that. And most of you understand this. This really has to do with the error involved with taking an analog signal and quantizing. And this is fairly important because that kind of error can really cause problems for the actual level of fidelity you're going to get with measurements. The second thing is, going through this, we're going to look at the exponential distribution. We're going to do problems, some problems. And I'm going to show you stuff with ways to find f of y from f of x without formulating the integral. And then hopefully we'll have time for some conditional probability. And I don't think you're going to have problems. And I'm looking at his notes for this. I could put them up, but I don't think I need to. Now, you all read through the uniform density, right? Can you understand, for the uniform density, you can find the average value by just taking the extent, the x1 and x2, the extent where it's constant, adding those two up and dividing by 2. That would be the mean value. You can find the mean squared value by just multiplying the constant density by x squared and integrating it. And then you can find the actual standard deviation by taking x squared bar, mean squared value, minus x bar squared. And you can find this fairly straightforward. So with the uniform density, there's one thing, and this is analog to digital. It's in his book, and it's also in the note set. This is A to D conversion. So first of all, when we're talking about this, we have to make some assumptions. If we assume that the signal that we're going to quantize or go to a digital domain, we have to assume it's got a constant, where we have to know something about the probability density function for this value. So if it's x, then let's say it goes from 0 to, matter of fact, the way he does it, he goes from minus delta x over 2 to delta x over 2. This is just a range, and then the height has to be just 1 over delta x. He's trying to make this as simple as possible. I hope you understand. This is just, typically x would represent a voltage or something like that we're going to quantize. You all with me on this, class? Yeah.
Is this chapter 7?
No, we're not in chapter 7. We're in section 2-6. Chapter 2-6. Chapter 2-, it's right after 2-5. Did you look at this?
I think it's 2.7.
It's 2.7.
This
Because the 2.6 problems were not A to D conversions. Wait.
Yeah, 2.7 is the uniform.
Yeah, it's the uniform.
Oh goodness, I couldn't tell you.
2.7 or 2.6?
It's 2.7.
2.7.
2.7.
Okay, hold it.
Wait a second. I'm not going to question you. You're probably right. 2.5 is Gaussian.
Really?
The 2.6 is analog, right? That's what I'm saying.
I think
Rayleigh
Rayleigh
does-
It's Rayleigh and Argasian.
Well, they have Rayleigh, they have the exponential, they have all this. They're constant, don't they? Let me
They
just,
separate Rayleigh and uniform.
all right, hold it. Other probability density. Oh,
Yeah,
never
it's
mind. That's 2.7. Sorry. This is, but, okay. Yeah, they do break it, and it's just other distributions. This is stuff, I'm sorry about that, I want to cover. And the only reason I'm doing this is because it's very applicable for a lot of engineering things that we're going to be doing. Okay, so if we're talking about this, and this could be a voltage, so this could be, actually, maybe I'll do it that way because it'll make a little more sense to you. And I'll just put this as a voltage f of v and call this delta v over 2 minus delta v over 2. And this height is going to be 1 over delta v. So this represents a voltage. And this is saying we're assuming the voltage is equally likely to have all values, and we're going to quantize it. So if we do that and we think, and in the book, I'm not sure where this is, but I want to give you a reference because it'll help you if you want to take a look at something.
Should be page 88, probably.
Okay.
It's like that first big paragraph.
Yeah, this is it, and that's, he shows us here. When we look at this, and here I want to talk mainly about the mean square value of the error, the RM, that Indel called mean squared value of the actual error in the quantization. So they have levels of quantization. What he actually does in the book is he'll show you a diagram, and on the vertical axis he'll have a signal, I believe. Well, I'll do it this way. He's showing you a signal. If this is, say, time, and this is voltage, this is an analog signal, and then these are the allowable levels. And so this signal itself, when it's quantized, will go 0, and then if it was quantized properly, it goes 0, and then it would be a hard change when this gets closer to delta V compared to 0, be a hard change, and it would become a staircase like this. And I think you understand that. That's just A to D conversion, right? And the number of levels you have of conversion depends specifically on the actual, or I should say, the value of delta V. As the delta V gets smaller and smaller, there are more and more levels that are allowable, and this is done in a binary format. So the usually 2 to the n levels allowed, where n is going to be an integer, and then that will give the total number. You take 2 to the n and divide it into the voltage dynamic range, and you will find the value of delta V. This will be pretty obvious too when you do something, but I just wanted to go through a few of the things. When you have this type of quantization error, what we really talk about, when we talk about error, we always talk about, think about this, the actual distance that you can make this is kind of strange. If I started here and I looked at error, right? If I'm at this point, and this is delta V over 2, this is delta V, right? The total range from here to here is delta V. Do y'all follow me in this class? All right. So when we do error, and we're talking about quantization error, what we have to do is take a look at how would you define error here? Well, if this is a voltage V, the error would be, you could do it 2 ways. You could either take V, you could just look at the error up here, minus delta V over 2. You could take that and square it. Now that'd be a squared value right there of the error. And then you can multiply that by the probability. And if we only go from here to here, then the probability becomes 2 over delta V. What I'm really trying to show you is if I go from here to here, just in this range, that means this density function will have twice that value. You all follow me? But I can make arguments that will be symmetric down here, so it's not a problem. I have that, and then I'm going to integrate this dV from 0 to delta V over 2. This is one way to do it. And you would get, in this case, it would be the actual error, and it would be what, delta V squared, it would be the mean squared error. You can also write this out, and these are symmetric and identical equations. It can be 2 over delta V here, and you can go from 0 to delta V over 2. This is the way the book does it. And you can just take V right here and square it, dV. Now this is the way he does it in the book. These have identical answers. The only thing you need to do is a substitution of a variable. You can make x equal to V minus delta V over 2. Delta V over 2 is a constant, and that means dx is dV. It's just a substitution. Do y'all follow me, class? These will have identical values. So if you look at this, this becomes 2 over delta V, and then you get V cubed over 3, and it's from 0 to delta V over 2. So now I put in the values, so I have 2. I'll try to make this clear. I'm not going to spend too much time, but I do want to make this point. 2 delta V over, and then you get 1/3. And when I go from 0 to delta V over 2, well, this is going to be delta V over 2 cubed, so it's delta V cubed over 2 cubed is 8, or I can just put 2 cubed. So this comes out to delta V squared over 12. He has that. And that's the mean squared value in the error of the voltage. Quantization error, I think he calls it, right? So then, typically, I mean, this is going to be the key aspect of this. There's a problem I gave you. I'm very, very aware, folks, that you're focused on the quiz, but you're going to have to work with me on this one because we have to cover this material. So if you look in the book, and I want to say it's 2 point. We could do a couple of these. Actually, you know what? We can go right to the problems in the chapter, or the examples in the chapter. We'll do. So if you look at on page 91, exercise 2-7.1, we can do the problems in the back of the book. I'm going to do a few of them in this section, but I just think that it's important, at least you see this apply to a problem. So the only thing I'm doing is I get the mean squared error there, that's it. And I want this portion of the board available. Now we're going to apply it just to some simple exercises in the book or examples. Actually, this is an exercise with answers but no actual solutions worked out. So for that one, 2-7.1, can you tell me what that is?
A continuous signal that can assume any value between 0 volts and +1 volts.
Plus 1?
10
10
volts.
10 volts.
Of the decimal.
Okay.
With equal probability is converted to digital from form by
ADD.
quantizing.
Quantization.
Quantizing.
Quantization. Go ahead.
How many discrete levels are required for the mean square value of the quantizing error to
L
be
squared over 12. Go ahead.
0.01 volts squared?
Now, you got to understand, this is volts squared. That gives it away that you're dealing with error, quantization error. If it was volts, it's different. Y'all follow?
Okay.
Delta V squared would have a V squared thing. So they give you 0.1, right? 0.01, is that right? All right, now, right off the bat, we can get delta V, right? Did anybody look at this? Did you look at it?
I looked at the problem, but
All right, well, just work with me and make sure you follow the logic. So for this one, that means if I look at this, delta V itself is equal to simply going to be the square root, and that's 10 to the minus 2 times 12. So what is that? 10 to the minus 1 times square root of 12, but can you just give that to me? The value. It's just take 12 times 10 to the minus 2 square root, or
0.346.
all right, keep that there. 3, 4, 6. Now, if I take a look at this, the number of levels I get, this would be n levels. You can get n by taking the range, the dynamic range from 0 to 10. It's just 10 over 0.346. That would be the number of levels. Do y'all agree with this? If we know delta V and we know the total range, we take the dynamic range, that's the total spread in the value of voltage. Now, if it went from minus 10 to plus 10, it would be 20. Do y'all hear me on this one? So it's the dynamic range, the total spread. And what do you get for this? 28.90. Now, a 0.9 level doesn't make sense. It would be 29. Does he have 29? Because I don't know.
He doesn't.
Yeah.
Oh yeah, he's
Yeah.
got 29. Yeah.
All right. So the next part is, anybody.
If the number of discrete levels is to be a power of 2,
Now this is important. Guaranteed you'll get questions related where it has to be a power of 2, because that's when we do binary anytime you get into digital signal processing, all the real information is stored in binary format. So here, I've got 29 colors, right? 29 levels. Now, if you think about this, it has to be 2 to the n. 2 to the 4th, 16, 2 to the 5th, 32. It has to be 2 to the 5th. Do you agree with that? You follow me on this? With me? So now we say the new, now I'll call it n prime here. The number of levels is going to be 2 to the 5th, or 32 levels, right? Now, once we have that, now we figure out the delta V associated with this. Because the natural question is, now what's the error with this? And if you take I think that's what he's asking. Isn't that the next part?
If the number of levels of part B are used was the actual mean squared quantity.
Does he say 32? Let's try that.
He says 32 in his
Okay, now if that number of levels, now find the delta V first. So delta V would be what? You tell me. What's the dynamic range?
10.
N divided by the number of levels, or not number of levels. We got to do what?
You gotta,
We got to find the delta V. I'm sorry.
right,
And that, you don't, that's the typical mistake. You all follow me on this? So what's the delta V for this new, the new N new? The delta V itself would be what? It would be 10 divided by 2 to the 32, correct? I mean, not 32, 2 to the, sorry, it's going to be, for this case, it is going to be 32, right? Sorry, I had it right the first time, didn't I? So what is that? I don't even know.
0.3125.
Pardon me?
0.3125.
3125? It should be less than before. Yeah, it is. Okay. Now, do they want the mean square? I'm sorry.
the actual mean squared quantizing value. Error.
Yeah.
Mean squared error, right?
Yes.
Quantizing. All right, so it's going to be this delta V squared over 12, correct? It's over 12. So this is, I believe this is right, but I'm going to tell you, I'm not sure. What is that?
Zero, zero, something.
0.0086.
Is that what the book is?
You didn't put an answer for that one.
0.003 is what
You should.
it says. But he put them all out of order.
Yeah, because for the first one.
Well, what is this again? What is this area?
I think the answer is he's got, because 29 is the first part of the 32.
They don't, they're not in the right order. Never are. But what is this right here? Just tell me what this value is.
0.008614.
0.0086?
1
One what? 1 4. Is that what he has?
No. Yeah, 0.003. I think that's what we got the first one. Yeah, 0.34.
For what? Wait a second. What? That's the right answer.
But he has, he has 29 and 32.
How's it get 0.002 from that? I think that's right. That's right. All right, and I want to tell you one other thing about this. What was the mean squared error to start with? 0.01, see that? All right, this has to be less, there's more levels. And it is less by a little bit. It's like about 0.861, the original error, if you look, right? Follow me on this, guys? All right. I wanted to do that problem for starters. Now, these are on the notes, so I'm going to ask you, you haven't looked at it, don't worry about it, but I want to do this one also, just to really make it clear. So for this one, we're going to have a signal that can have a dynamic range from -8 to 8. So the signal has a range, the V has a range of greater than or equal to -8, less than or equal to 8. Then, how many quantization levels are required at least to ensure that the sigma x squared, the mean squared error. Now, can you see the average value on this signal right here is going to be 0? If it's from -8 to +8 with an equal probability, it's 0, right? And that means that sigma x squared is actually the mean square of that, well, of the voltage, actually. Right? So how many levels are required if you want a mean square of, I think it's 0.01, but I want to be sure about this, 0.01. So I want the number of levels, and then we'll get it in power of 2, just to make sure everybody knows. So it's exactly the same thing, isn't it? What do we do first of all? Well, what does this represent? 0.01 represents what? Delta V, right, squared over 12, correct? Isn't this about identical? So that means delta V itself is what? 0.346, okay? Right. Now, how many levels for this one? Now we have a total dynamic range of 16 over 0.346, and what's that? 46.2. Y'all ready? If it has to be a power of 2, all right, if the number of levels have to be a power of 2, and have at least that resolution, what's the next power of 2? 3264, right? So now you would have n equals 64, correct? If we want a power of 2, I'll call it n prime would be 64, and that would be 2 to the 6, would it, class? So we have 6 levels. Now, what is the new delta V going, or I should say, what is the new delta V squared over 12, which is sigma V squared? That would be mean squared error, because that's, I can put that down there because, in fact, the variance is the same thing as the mean squared value because the average value is 0. Correct, class? What do you get for this? Well, we better get this. We have to get this. So if we say delta V would be what? It would be 16 divided by 64 squared divided by 12. What is that? 1/4 squared 16. So 1 over 16 times 12 would be? Yeah. You got that? This doesn't seem like much, but believe it or not, it'll get you at least going in the right direction when you have to do this. Have you taken digital signal courses? Yeah. Did Dr. New talk about A to B conversion? Did he do there? Something like this, did you see or not? Mean square error?
No.
What are we talking about? This is actually 7.
The exercise is because of lots of them.
Is that 272?
272.
What is that from? I'm looking at it on the PowerPoint.
I don't think that's specific problem.
It's the form of the problem.
Yes.
The type. I want to talk about the exponential decay next. And the reason is that this is a very, very common thing. And I mentioned to you that the exponential decay, the only thing you need to do is when the information you want starts and when it ends. That's not really suitable, I mean, the way I explained it just there, but you have to see this example. So remember, there's all these density functions that have to do with something in the natural environment. If it's Gaussian or Rayleigh or Maxwell-Boltzmann, the exponential type of density occurs all the time for failure of devices, guaranteed. So what it says is this. If you take a look at the mean time to failure. When you look at this, if this is time, you're going to get a distribution that does this reliably. Now what this is f of t, he'll have f of tau there. And that's 1 over, and it's tau. And tau is going to be the mean time to failure. And this value is going to be 1 over tau here. And if you look at this, when we talk about this, what does it mean? It means the probability of something failing from 0 to t. I'm going to try to put this down here. So if something's going to fail between the time it starts and time t, it would be the integral of this, f, what I'm calling just f of t dt from 0 to t. And I'd have to find this. And when you do this, this is an exponential right here. I can write down the whole thing. It's going to be exp to the minus t over tau. And this is times u of t. So this is only good for t greater than 0 for this function. But we're going to extend it so what we can do is apply this to all manner of things where you're going to have the likelihood of something failing is given by this. And what's the probability that no failures, or that no failure occurs for 1 second, and that there's going to be no failure from that point to 5 seconds. Now, you're going to have to see this worked out to appreciate it. What this integral becomes is this 1 minus exp to the minus t over tau. And what this is, the probability of it failing between the time this event starts, which is assumed 0, and the point of observation of t, right? And it's just the area under this curve. Right, that's the probability of the event failing. The probability it doesn't fail would just be 1 minus that. You all follow me, class? Now, the thing about this is, this particular type of thing, you get device failure. The failure, if you have something where you have a device or many devices, if one fails, it has no bearing on the statistical information of the other fail. Now, you're going to have to see this applied to really appreciate it. In his book, he talks about it, but you won't see really the ramifications of it until you see it worked out. So here, actually, you have my book. There's several problems I was looking at here. I'm trying to make my point clear. Exercise 2-7.2.
Setting up to a television set as a picture to with a mean time up to failure 10,000 hours. If the set is operated an average of 6 hours per day.
Hold on. So it's 6 hours per day. Go ahead.
What is the probability of picture 2 failing within the first year?
Okay. Now, what we need to do is figure out first how many hours are in a year. So to take a look at this, 6 hours per day, so total hours in 1 year, I'm just calling hours per year, is going to be equal to 6 times, it's really what, 365.24, something like that, right? You got the leap year for you. So what is this going to be?
You want to include those people?
Why not? It's gonna be an estimate anyway.
2,191.44.
So what's the probability it fails the first year? Isn't that what he asked? Think about this. This is the probability of failure from 0 to t. T would be 1 year, right? Or as t would be, in this case, 10,000 hours. I'm sorry, t would be 2191.44 hours, correct? So that means the probability of failure in the first year fails in the first year is going to be equal to 1 minus just the integral of that f of t from 0 to the point of failure, not 0, and it's going to be exp minus 2194.44 over 10,000, right? And what is that? Hopefully we're getting close. I haven't done all the problems about this, but they're all the same. Don't do my stuff. Remember these things?
Yeah, they're all pretty easy.
But there's something that's going to happen. What did you get for this?
0.196.
Is that the answer? One of the answers?
Yeah.
Okay, that's the first part. Now, the next part is what? Next part of the question.
The next part of the problem is, what is the probability of no failure within 5 years?
All right, how do you do that one? Now look, this is the probability it fails. Right? Matter of fact, this is the probability it fails from 0 to t. The probability of no failure would be what? Probability of, and I'll just call it no failure to time t would be 1 minus that, right? You can see it really comes down to a simple expression. Minus t over time. Y'all agree with that? That's just what? exp to the minus t over tau. Isn't it class? So within how many years? 5. All right, now we've got to find the number of hours in 5 years, right? So now we have to take, to get the time t that's going to go in here, t itself, because we've got the other thing in hours, is going to be 5 times the number of hours per year, which is what, 2191? So 2191.44. I don't know what that is. All right, that means the probability of no failure within 5 years, no fail in 5 years is equal to this one, exp to the minus, I'll just put it as 5 times 2191.44 divided by 10,000, right? And hopefully you get the right answer. Pardon me?
0.334.
Is that right?
35.
The 0.443. He didn't add, I don't think, I'm sorry, he didn't add, I don't think that 0.25 for each year. But I looked this up, you're supposed to, or 0.24 something 41, if you want to be an actor. But this is, again, we're just trying to show you how you operate. The last part's the important part. Now, remember what I told you, that the only thing that matters when it comes to probability of failure is when the event starts and when it ends, right? Of the event we're interested in. So the next part, say it again.
The second part?
Third, I mean, there'll be a third part to that one, isn't there? That's not the right one.
There was a problem with the homeowners that had to be replaced. With the light bulbs, which is 2-7.4. 3 was
Oh, yeah.
7.3. Oh.
All right, hold on. I want to get through this one. There's two other things I want to. What is it? Is that an exponential decay?
Yeah, it's got the mean time to failure.
Yeah, that's-
7.3 is the mean time to failure.
Yeah, let's do 7 real quick. And I don't think it's hard, but there's one aspect of this where it says if the device doesn't fail up to a certain point, what's the probability it fails at another point? Kind of, or what is the probability of failure occurring, and he'll give you a specific interval, or no failure. For this one, let's do this. So this is 2-7.3, but this is the problem, right? So go ahead.
Okay. A communication satellite is designed to have a mean time to failure of 6 years.
It's not good.
Okay. If the actual time to failure is a random variable that is exponentially distributed, find.
Now we say this. Now we've got this. This is the f of t. Mean time is going to be 1 over t exp minus t over tau. Go ahead.
The probability that the satellite will fail sooner than 6 years.
This is straightforward if you think about it, isn't it? So I know the probability it fails. This is probability of failure from 0 to t is going to be 1 minus exp minus t over tau. They want the probability that no failure or failure.
That it's going to fail sooner than 6 years.
Okay. And this is pretty straightforward. This is part A, I guess, of that problem. It's going to be 1 minus exp to the minus 6, and what's the 6 years, right? 6 over 6, so it's just 1 minus e to the what? E minus 1. Is it class? What is that?
0.632.
Is that right? I know I posted the answers. Is that right?
Yeah, that's right.
Yeah, that's right.
All right, next. Next part.
So the probability that the satellite will survive for 10 years or more.
Can I just make sure I have your answer? How would you get that?
1 minus 10.
And what is it really going to be? Isn't it just this?
You wouldn't do the 1 minus.
I mean, but that's it. It's 1 minus it. So it's plus the exponential. The ones kill each other. So for part B, the answer itself is just going to be 1. Probability that it doesn't, it's what? 1 minus that, so it's going to be simply what? EXP, what was the time? 6 years?
10 years.
10 years, so it's going to be
Or,
what?
tau, the mean time is 6 years.
Yeah, it's 10 over
10 is,
6.
yeah.
What is that?
0.188,
Is
or
that-
1.896.
0.189, is that right? All right, now the next one, I think this is the one that has this too.
Yeah, so the probability that the satellite will fail during the 6th year.
Shoot, this is the one I'm thinking. All right, how would you calculate the probability it fails within the 6 years? Do reason it through it.
You have to find limits.
First, what would you do? Think about the limits. 6th year, right? The beginning of the 6th, into the 6th, start of the 7th, right? So how would you do it?
Go from 5 to 6.
Probability, what? That, you could say the probability, I'm trying to cast this in a way that makes sense. Look, if this is the distribution for failure, right? The probability it fails between any 2 points, A and B, is just the area under that curve, right? Just think about logically. All right, so if I want the probability, this is part C, right? Probability it fails in 6th year. And this is all years, so what would it be? It would be the integral of that f of t prime dt, right? And this would be from 5 to 6, wouldn't it?
Yes.
What's that going to be? That's going to be exp, right, to the, and this would be minus 5 over 6 minus exp to the minus 6 over 6. Isn't that right? Y'all follow me? When you do the integration, you're going to get a 1 minus that business if you take it. I mean, really, here's what happens. When you do this integration right here, if I integrate 1 over tau exp to the minus t over tau dt from A to B, right here. Now I get 1 over tau. The integration of that is going to be tau, and be a minus sign, right? And then it's going to be exp minus t over tau, and you have to evaluate it from A to B, right? So you just reverse the limits because there's a negative sign. These two cancel, and you're going to get e to the minus a over t, since a is less than b, minus e to the minus b over t. And what do you get for that, by the way?
1, 2, 6, 6, 7.
Is that the answer then?
Yeah.
But it's important to see that, because you can get kind of confused now. There's one, is the other problem the one I'm thinking of? No, wait, hold on. Can you just read it real quick?
Homeowner buys package containing 4 light bulbs, each specified to have an average lifespan of 2,000 hours. 1 light bulb is placed in a single bulb table lamp. The remaining bulbs are used one after another to replace one that burned out in the same manner.
Did you guys do that? All right, the one I'm actually looking for is an IC thing. Is there an IC problem in
There's the IC, that's the continuous signal voltage between negative 20 volts and plus 20 volts. That's the IC.
there? It says, this is the one I'm looking at. It says exponential distribution. Actual time t is a random variable with an exponential density function, right? What's the probability that the thing doesn't fail after 4 years? Okay, wait a second. I'm going to try to say this and get this out of the way. This is kind of. Where I'm looking at to get this information, I'm looking at the PowerPoint. This is what I wanted to try to showcase to you. So with the exponential distribution, suppose we have an IC integrated circuit, and it has a mean time to failure of 4 years. You have an IC, and it has a mean time to failure of 4 years. Now, what is the probability that it survives past 10 years, given that it survived to 6? So what I want is the probability that this IC survives greater than 10 years. Given it survives 6 years. Everybody with me on this? This is a great problem. Right? This showcases what I want to talk about. So if you think about this, it's saying it's like a conditional probability. It said it made it to 6 years. If it's made it to 6 years, the only thing you care about is the distance from 6 years to the point of failure. All right? That you don't. This is one of the problems you get into. You can prove this mathematically, by the way. When you have these things, remember the probability of failure is like so, right? Call this, let's say this is 0. This is the probability of failure of that device, which is e to the minus, or this is the density function, and it's 1 over tau, e to the minus t over tau, u of t, right? So that's the density function. It doesn't fail all the way to 6 years. So it says it made it that far, right? Now if it made it that far, It means the probability fails. The area under the curve from here out to infinity has to be 1 as well. Do y'all follow me on this, class? If it's already made it that far, then the probability it fails from 6 years to infinity has to be 1, right? If you integrate this curve, you're not going to get 1. You all follow me? So what happens is at this point, this is the way I explain it. I'll show you more about this when we get into the conditional probability. You simply take that point right there and then take this whole thing and move it over. So now you start from 6 years instead of the actual 5. And now you go out to here to, it's 10 years. This is my point, right? Well, the probability it fails from here to here is the same thing as if it would fail between 0 and 4 years. Do y'all follow me, class? Or not? No? The reason is see, in this, I'm not saying this, you can prove it mathematically because we can talk about a Venn diagram of this, but I'm trying to do this in a way that, to me, it makes it more obvious. If you tell me it didn't fail at this point, and I know it's exponentially decaying, I mean the rate of failure from that point, that means it's going to fail from this point to infinity. It means the area under that density function has to be 1. And it also means, because of that, and because it's an exponential decay, I can effectively just take this whole thing and shift it to that point. And now if I want the probability it fails or doesn't fail from 10 years and up, but I really look at this distance right here, which would be 10 minus 6, and that would be the time I'm worried about calculating, either a failure between years 6 and 10 or a failure between greater than that. You all with me, class? And what I'm really getting at is anytime you have an exponential decay type of event, so the probability of failure is exponential decay, the only thing you need to do is look at when was the last, if they give a conditional probability. If it made it to 6 years, you literally start there and make it. They can just shift the entire distribution to that point. Y'all, does that make sense to you? That's all you have to do. He has in the book, I thought there's a problem in your text on that too. All right, hold on. Problems. Anybody have a question about any of the homework problems? I'm going to do the 20 minutes? Yeah, go ahead, Brad.
I couldn't understand how to do like when you have a Gaussian, so 262, and then you have another function saying like y equals x3. I didn't understand how to find the probability density function.
Wait.
Given fx, basically.
No, I mean, for all these, what's the key thing? There's only one thing you need to know. Whenever you do these problems, if we need an f, we need to get the f of y, right?
Mm-hmm.
So it doesn't matter which. It's problem 6.
Yeah, 2.6-2.
The only thing, remember how we did all of what we'd say if we have, say x is a Gaussian random variable, right? And it can, it's got a mean of 0 or not.
Mean 0, yes.
Right, if it's x is 0, right, then for a Gaussian random variable, this is going to be kind of sweet, right? Because you know that what? Sigma x squared is x squared bar, then, right? Correct? If you got a mean of 0. And so if you want, you got any function, I'll call it y is equal to f of x, right? And that means x is equal to, you can say it's y to the minus 1, the inverse function of that. And that would give you x, correct? So if I want the probability, or really f of y of capital Y, random variable less than small y, that's the same thing as y. F of x, right? And now instead of y, it's going to be of the associated value of x. First of all, do you remember doing this or not?
And not Gaussian.
I mean, it wouldn't matter what
Like
distribution.
general
I'll
Yeah.
play for the last three.
Yeah, but it doesn't matter what the distribution function is, does it? The only thing you need to know is if you're gonna come over here, you have to put the right limits, right, over here. So for this one, for f of y less than y, right here, is the same thing as y. It would be of x, or I should say of x, and then you would less than what? Y minus one, the inverse, correct? Remember doing this?
It's asking for the probability density function.
But I mean, do you remember doing this?
Yes, I
This
remember
is,
that,
so
yeah.
then, what do you do to get the density function f of y? You would take a derivative of this, right, f of y of a random variable of y less than or equal to y of y, which is gonna be the derivative with respect to y, right, of this, f of x less than y minus one. Well, what is the derivative of that? Remember, you set up the integral, right? Here, you set up the integral as d dy, and you have the integral, if it's Gaussian, a Gaussian integration, right? And if you've got a squared or a cubed or something like this, you have to have the right limits. It could be from like square root of y plus y, minus square root of y to square root of y. This is the one you did, I think, right? You remember doing this? And then what would you do? Now you've got to put in the Gaussian variable there, right? I mean, or whatever function is, then you have f of x, and it's dx, and then you have to go through and evaluate. Then when you evaluate this, you take the evaluation of what? Take f of, and then the square root of y, or whatever the functional relationship is. Correct, class? Do y'all remember? You remember doing this? The only thing you're doing is taking this value, putting it in here for the f of x function. Doesn't matter if it's Gaussian, Rayleigh, Maxwell Boltzmann. And then you have to take a derivative of that with respect to y, right? Then minus, then it would be minus, which makes it a plus, the value of f of square root of y at the lower limit times the derivative of this. And that's going to be 1 over 2 times 1 over square root of y, right?
So we have to memorize the Gaussian function? So we have to memorize that. 1 over square root 2 pi times sigma, all that one.
But I mean, it's giving you a what? A mean is 0, right? What's the standard deviation?
1.
It's 1? Then the entire Gaussian function is 1. If you're telling me f of x and mean value is 0 and sigma
Sorry,
is
not
1.
standard deviation is, well, yeah, actually, in this
That's
case,
a-
the standard deviation is 1.
All right,
That's
so
a
then
normalized-
it's just 1 over square root of 2 pi, right? That's good, because the sigma is 1, e to the minus, and then the x squared, whatever it is, over 2, right? That's, I'll give you that if you want, but it's straightforward. You agree with this? I'm kind of pressed for time. Let me give you a quiz. So separate yourself, you know the drill.